Okay, binary addition. Over here we have a base 10 inverted commas normal addition. So if we just run through this quickly to look what the behaviors are in terms of what happens when we add numbers and what happens to the columns. So 5 adds 7, well, that gives us 12. So what we do is we put the 2 down of the 12 and we carry the 1. Now when I was taught, we put them at the top, so there's my carry. So we've got the number 12, the result of 5 plus 7, the 1's up here, the 2's down here. So we use that carry in the next addition, so 1 add 7 is 8, add 5, well that gives us 13, so we put the 3 down and we carry the 1. Now that 1 is hanging out on its own, so it just falls down to here, gives us 1, 3, 2. Binary addition has the same behaviours, this notion of carrying if we can't fit the number in a particular column. So if let's quickly have a look at all the conditions that we can get from adding binary together. That gives us this little table over here. So 0 add 0 is 0, 1 add 0 or 0 add 1 is just 1, 1 add 1 is 2, and 1 add 1 add 1 is 3. Okay, so these are all obviously in binary. Now if we do 1 add 1, we get 2, so that's 1, 0. So we put the 0 down and we carry the 1. Now that carry flows into the next addition, which is 1 add 1, well that's 2 again. So 0 and carry the 1. 1 add 0 add 0, well that's just 1. 1 add 1 is 2, so 0 carry the 1. Got 2 again, so 0 carry the 1. 2 again, 0 carry the 1. 1 add 1 is 2, so 0 carry the 1. And this 1 add 0 gives us just 1. Okay, so that falls down to there. Okay, simple enough. Let's move on to another example where we have a 1 add 1 add 1 case. So here's the addition. So again, it's just with the base 10 addition, it's 1 add 9, which is 10, so 0 carry 1. 1 add 9 add 5 is 15. So we do the 5, carry the 1, and that falls down to there. So 1 add 1 is 2. So 0 carry 1. 1 add 1 is 3, so it's 1 carry 1. 1 add 0 add 0 gives us 1. The next one is just 2, so 1 add 1 is 0 carry the 1. 1 add 1, we've got a 3 again, so it's 1 carry 1. 1 add 0 add 1 is 2, so 0 carry 1. 1 add 1 add 0 is 2, so 0 carry 1. 1 add 0 is 1. Pretty straightforward. Now the next example, we're going to have a situation where we have something called an overflow happen. So let's watch this evolve. The addition, as before, is pretty simple. The answer should be 260 when we get to it. So 1 add 1 is 2, 0 carry the 1. 1 add 1 is 2, 0 carry the 1. 1 add nothing is 1. And then 1 add 1 is 2, so 0 carry the 1. 1 add 0 add 1 is 2, so 0 carry the 1. Got 2 again, 0 carry the 1. And we've got 2 again, 0 carry the 1, and we've got 2 again. So 1 add 0 add 1 is 2. So we put the 0 there, and we would obviously have a carry, but this time that carry is going to fall down to there. Now there's a problem with this. When we ask computers to do additions like this, they're kind of constrained or confined to the number of bits. In this case, two 8-bit numbers being added together has resulted in a 9-bit number. So we've kind of gone out of the bounds. We've overflowed. Now this, to you and I, isn't a problem. But to a computer, this potentially can be a problem. In fact, we call this an overflow error. Now, if you want to find out real-world consequences of overflow errors, not quite the same as this, but the result of something called an integer overflow. If you look at the Ariane V8TA incident, I think from 1996, that will show you how this, not anticipating this kind of addition can actually cause real issues. Okay, the next bit is just an illustration using a simulation as to why managing the carries matter and how the carries actually function in a computer when it's doing addition. This obviously is still just an abstraction, but it's quite an insight to what's happening under the hood. So just to orientate ourselves, what we've got over here on the right hand side is the ones column 2, 4, 8, 16, 32 and so on at 128. And currently we've got an addition set up which is just all zeros added to all zeros, which gives us, well, zeros. Now this number here, this 0, is matching up with this guy here. So that is that. The next 0 along is this guy here. Okay, the next 0 along is this guy here. So we've got an 8-bit number here, and we've replicated that with 1, 2, 3, 4, 5, 6, 7, 8 bits on this side. Underneath it is the second number, and that is represented down here. So this is the second number. Currently it's set to 0, so none of these are turned on. If we were to flick this switch on, that would be a 1, and that would be that 1 there. And this is the product, or this line here. So currently it's just all zeros. Now, one thing I want you to kind of look at in this is the notion that we've got this 0 hanging out down here. This is kind of an unstated rule that we learn when first learning how to do addition in base 10. So when you do the first addition in this column, you always start from the right hand side. There's never any carries that come in from previous additions because there are no previous additions. So you never have a carry coming in here. If you think about it, you can only have a carry from this column onwards. So there's never any carries coming in. That's what this thing here is doing. So it's saying that there's no previous additions, there's 0 being carried in. That's what this C in means. So nothing is being carried in. Okay, so that gives us our setup. So let's move actually into the simulation, which is here. So again, we've got our 1s column, we've got our 2s column, 4, 8, 16, 32, 64, 128. Now currently, if we set this up to, let's say the top number is going to be 0, 0, 0, 0, 0, 0, 0, 1, add nothing, well the answer is 1. So if you look at this, we've got 0, 0, 0, 0, 0, 0, 0, 1. Okay, so 1 add nothing is indeed 1. If we do 1 add 1, well that's 2. So that is 0, and if we look at this, we are carrying the 1 into this column, and it pops out there. So that gives us our answer 1, 0. Okay, so let's do another one. Let's do 4. So the top line is just the number 4, and the bottom line is going to be the number 3. So if we do 4 add 3, well that gives us 1, 2, 4, which in this case is 7. Let's do one more. So if we do 16, add 8, add 2, add 4. Okay, so let's do 16, add 12, 13, 14. So if we look at this, we've got 16, add 8, add 4, add 2. Pretty straightforward. Okay, so the reason I set this up is that we want to see what happens when we have an overflow error. And what I'm going to do is simply add 128 to 128. So 128, that reads perfectly. So 128 add 0, fine. But if I add another 128 to it, suddenly I get nothing. Okay, so seemingly what's happened is we've added 128 to 128, which should give us 256, but the product, according to this 8-bit adder, is that we get 0. The answer is 0. Well, that's not right. If we try again, and let's say we do 132. So 132, add 128, well, that's 4 apparently. So what's happening is down here, we should have a carry, but it can't go anywhere. There's nowhere for it to go. So that essentially is an overflow error. That 1 has nowhere to go. It overflowed and fell straight off. So what we're left with is an incomplete addition, or an addition that looks like, well, if we add 128 to 128, we get 4. What we can do is we can rescue that overflow. So if I bring this in, let's just pop it there and connect this up. So there we can see the overflow. Now, if we had a 256 column, we had 9 bits, then that would work out correctly. Okay, so that's an illustration, firstly, of how computers would add machines. Inside each of these, we've got the circuitry to actually do the addition. And we need to keep an eye on overflow errors.